All right, so I'm going to describe to you, so now the general result of all this work we've done, looking at the interacting fields, the Dyson expansion of the S-matrix operator, the implications of Wick's theorem. Everything can be summarized, all the results of the perturbation theory for the interacting Dirac electromagnetic fields can be summarized in Feynman rules, which is what we're going to be doing today. So, just to remind you the background, the state of time t is plus infinity is the S-matrix operator acting on the initial state, and we have the transition amplitude to go from the initial to the final state. If I measure the final state, the probability or the probability amplitude that I will get the final state F is equal to this S-matrix element. And we have, so the probability is of course modulus squared, and we've seen that when we have the Dyson, well, the Dyson expansion this operator is expanded the series 0th order plus 1st order plus 2nd order plus 3rd order. Okay, now what we've seen is this contains the, if you look at the Dyson expansion, the first correction contained one factor. In the interaction Hamiltonian density. This contains two factors. Okay, under the integral sign, there's a time-ordered product with of these products of these different factors. This contains three factors. Okay, so we have a series of terms, and of course each of these factors is proportional to E. So this is proportional to E, so this is an order E, this is an order E squared, this is an order E cubed. And remember, the fine structure constant alpha is proportional to E squared, depending on your units. And alpha is approximately 1 over 137. When you calculate the probabilities, you get an expansion in alpha, which is small, so it's a perturbation expansion. So the effects of these terms gradually get smaller. So now we saw that S1, which is IE, the integral over space-time of the normal product of psi bar, gamma alpha, A alpha psi. This gives the basic vertex. If you look at its contribution to the matrix elements, you get the basic vertex. So let's just write it like this. Get the basic vertex. What is going on here? So this can annihilate another. So if this, for instance, here's an electron, here's a photon. This can annihilate an electron. This can create a photon. This can create an electron. So it contributes to this matrix element. And plus all the different ways of twisting this around. So all this kind of thing. Electron, positron, photon, etc. But from the topologically, if I take this basic vertex, there are just different ways of twisting it around. But there's one vertex where you have two fermion lines meeting at a photon line. So that gives you the basic vertex. Now what happens from Wick's theorem is that the upshot of Wick's theorem is that, well, okay, the first order factor gives you the basic vertex. What does the second order factor give you? It gives you all ways of joining two basic vertices. So this gives you all ways of joining two basic vertices. Whereas the third order term, what does it give you? All ways of joining three basic vertices, etc. So, let's look at some examples. So, for example, examples. So, examples from the second order term. So, the second order term, well, so we've looked at one. Hopefully, you did this homework where you showed that, well, S2, there are a series of terms in the second order term. There's a number of contributions. One contribution, remember, Wick's theorem, you expand. This gets expanded into a sum of normal products, and each of these normal products corresponds to a certain process. And these processes, the nice thing about the Feynman diagrams is that the sort of awkward algebra of Wick's theorem, which is not very intuitive, can actually, the result of it can all be summarized by this simple result. So, for instance, so this second order term, what kind of process does it contain? So one process it contains is, well, let's say I take this basic vertex and let's take, so what do I mean when I say join, all ways of joining two basic vertices? Here are two basic vertices. Okay, here's one and here's another one. Let's join them. There we go. This appears in the second order term. And so this could be photon scattering of an electron. And there's also a related term which looks like this, where join, let's imagine, I take this term, this here, this basic vertex, and I take this basic vertex, and I join them. Okay, and I let this go here, this go like this. So here I've got photon coming in, electron coming in, electron coming out, photon coming out. Notice something, I think someone pointed out to me in an email, something maybe I said maybe sounded odd. Is remember we were saying in the normal product, here you have to annihilate the incoming photons, particles, and here you have to create the outgoing particles. Okay, first you annihilate these, then you create these. That is equally true here. First you annihilate these, then you create these two. Okay, that's the same thing, the normal product. You annihilate these first, and then you create these. From the point of view of the Feynman diagram, the symbolism, the way the momentum flows and so on, you get these two contributions where it looks as if, well, this is, from the point of view of the Feynman diagram, this photon is created before this one is absorbed. Okay, but that's from the point of view of the Feynman diagram. If you actually look at the normal product and the ordering of the operators, these still get annihilated before these get created. Anyway, that doesn't really matter. Anyway, there's this other, so the book calls this term SA and this term SB, if you're interested in looking at that. But now, there are all kinds of ways of combining. Let's take this basic vertex and this basic vertex, two basic vertices, and let's combine them. Now, conventionally, I should mention Feynman diagrams. It's conventional that time is going from left to right. It's just one of these things. So you've got sort of in and out. Now remember, these are Feynman diagrams in what's called momentum space. Feynman diagrams in momentum space. So really we're just talking about momentum flow. In the sense, well, I have some incoming particles with certain momenta, outgoing particles with certain momenta, and you know, the initial state is over here, and the final state is over here. So initial and final. So time runs this way in the sense that, well, here's the initial state, here's the final state. This isn't supposed to be a space-time diagram or anything, okay? This is really a symbolic representation of terms in a perturbation series. Anyway, if I join these two basic vertices, I say, well, here's my initial state, here's my final state. What have I got? This is electron-electron scattering. All right, I've got electron-electron scattering. Or I could also do the following. Now here's something, there's an awkward, one of the things that is a bit annoying about Feynman diagrams is that in order for this symbolic representation to work, if you're talking about positron scattering, let's say the incoming state are two positrons and the outgoing state are two positrons, then for this representation to work, this correspondence with the perturbation series, and we'll see exactly why in a minute, but you have to it's more convenient, anyway, it's more convenient if the lines on the fermion line, if the arrows are pointing backwards in time. Okay, so for positron external lines, the arrows point backwards. Now Feynman, back in the 40s, he actually thought of positrons as being electrons that are traveling backwards in time. He had a sort of intuitive way of thinking about this. But from the point of view of the quantum field theory, we'll see why in a moment. When you write down the Feynman rules, I'll explain, we'll come to it, exactly why it's best to have the arrows pointing backwards. But time is going that way, okay? This is just, we'll see, just for the moment. External positron lines, the lines go backwards. Okay, let's look also at, what else can we do? Let's, all kinds of things. It's just let your imagination run. Here is another vertex. Here's a vertex, and let's say here I've got an electron and a positron. So remember, the external positron lines, the arrow runs backwards. Here's electron positron. Here, that's one vertex. Here I've got another vertex. Electron and a positron. Let's join the two vertices. Join the two vertices. So here it looks like formally an electron and positron annihilate to form a virtual photon, which then forms electron-positron pair. Now, what happens, so here you can imagine electron and positron, you can think of them as colliding, annihilating, and then recreating again, or just scattering if you like. But anyway, electron and positron come in with certain momenta, electron and positron come out with different momenta. In all of these diagrams, with these vertices, there is always a factor. It's going to be one of our Feynman rules. And there's all, let me be using mu, let me use alpha. The book uses alpha here. There's always a factor. If you look at Feynman amplitude, the vertex always contributes an amplitude, i.e. gamma alpha. Let me just write it as i.e. At each vertex, there's a factor i.e., or really i.e. gamma alpha at each vertex. You will have seen, you've calculated, I hope, you calculated the matrix element for this process, and you showed that the Feynman amplitude here, there are the contributions, i.e. gamma at each vertex. There's also a contribution from the Feynman propagator on what's called the internal fermion line. Okay? And here, if you had an incoming momentum P and momentum K, this is evaluated at a form momentum Q, where Q is P plus K. Now, as I've emphasized, whenever you have a vertex like this, the sum of the momenta, if you write down, if you take it that the momenta are conserved, that the momentum along this line is equal to the momentum coming in, then this cannot be a physical momentum, okay? Because if k squared is 0 and p squared is m, q squared cannot be m. Okay, Q is what's called a virtual momentum. So it's a kind of imaginary, just a symbolic momentum. But in any case, when you work out the Feynman amplitude, there is a factor I times the Feynman propagator for the internal fermion line. This is a general rule. We're going to write down a list of Feynman rules soon. But whenever there's an internal line, there's a factor I times the Feynman propagator. Now you should have derived this for this case. You did the homework. This is a general thing, so a general result. Whenever there's an so here's an internal photon line, you get a factor in the Feynman amplitude. There's a factor I times the Feynman propagator. Similarly here, similarly here. We'll write down the Feynman rules formally a bit later on. Or other things you can do. Let's take this vertex and let's take this vertex. Sorry. All right, here are two vertices. Let's join them. So I've got an electron and a positron coming in, and I have two photons coming out. This is electron-positron annihilation. Okay, so electron and positron meet, they disappear, and you get two photons. The total energy of the two photons, of course, is going to be at least 2mc squared. Let's see, done that one, done that one, done that one. All right, so there's an example, there's some examples of what you get from S2. So, what about S3? Let's maybe look at, what is it I'm missing? Blah, 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 blah. So all of these come out, from the Dyson, with the Dyson-Wick expansion here. Said the result is that, well, all the terms that appear in here can be written down like this. There's just all ways of joining two basic vertices, and that is mathematically equivalent to the Dyson-Wick expansion. You want an example from, let's have a look at an example from S3. Let's look at S3. With S3, well, you might have something like, well, here you go. We'll just have this. S3. So S3, remember, there are three factors in the expansion, three factors in the interaction Hamiltonian. The result is that the amplitudes are generated by all ways of joining three basic vertices. So here I've got 1, I've got 2, I've got 3. So here I've got, say, 2 electrons coming in, and they scatter. So you have this one initial momentum, let's say P1, P2, and then P1 prime, P2 prime, and momentum K. So the 2 electrons, they scatter, and one of the electrons emits a photon. Or if you don't want to think about an electron emitting anything, you just say, look, the initial state, there are 2 electrons, the final state, there are 2 electrons and a photon. Okay? So here you have, there are 3 vertices. Each will contribute a factor I-E gamma. This internal line will contribute a factor I-D Feynman. And this internal, here you've got an internal electron line, will contribute a factor I-S Feynman. Let me just write you down one example from S4. So this series, of course, continues. Example from S4. Something actually I keep forgetting to mention. Let me just say it now. But if I look at, let's say I look at this process here, electron scattering. Each vertex has a factor IE. So the amplitude is proportional to E squared. So the problem, well, okay, let me write it like this. The amplitude is of order, the matrix element or the Feynman amplitude is of order E squared. So the probability associated with this process is of order E to the 4th. In other words, it's of order alpha squared. Okay, now remember alpha is about 1/137. For this process, the amplitude is of order E cubed. Of order E cubed, there's 3 vertices. So the probability is of order E to the 6th. In other words, it's of order alpha cubed. So, alpha is 1/137. You see successively, I add more vertices, these terms rapidly become much smaller. This is why usually, most calculations, you're just going to stop. You're just going to stop here. Maybe you go to think. Rarely that you go up to higher terms. You calculate. It's accurate. The higher terms are going to contribute just a tiny correction. Okay, so don't think, oh my God, I've got to sum all these infinite number of terms. No. Usually, most processes that you're interested in, just the first term or 2 is plenty. But here's an interesting example from the 4th order terms, is the following. Let's take 4 vertices. Let's take 4 vertices. And join them up. So I've got 4 vertices. And we're going to join them up and ask, well, what does this correspond to? I've got 2 photons coming in. I have 2 photons coming out. And here I've got what looks like some, here there is, you can think of this, I've got an electron running around, I've got this is an electron, positron, or whatever. Well, it doesn't, the distinction, the precise distinction of electrons and positrons is really just for the external lines. But anyway, you've got an internal fermion line, you've got what is called a fermion loop. A fermion loop. Now, 2 photons, this is photon-photon scattering. Now, photons, interestingly, they don't interact with each other directly. Okay, there's no, there's no interaction term. But what can happen is indirectly, you can think that the photons can interact with each other. So there is actually light can scatter off itself. Okay, this is a prediction of quantum field theory, but it's something, so in Maxwell theory, say if I have, say, 2 plane electromagnetic waves come in, in empty space, they just pass through each other, there's no interaction. There's a small self-interaction in the electromagnetic field. If you look at this process in the classical limit, it actually gives you a small nonlinear correction to Maxwell's equations. There's something called the Euler-Heisenberg-Lagrangian. You get a small correction to Maxwell's equation. This is a real process, but it's very small. So the amplitude is of order e to the 4th. So the probability is of order e to the 8th. In other words, it's a 4th order in the fine structure constant. So this is a very small probability. It's a very, very small process, but it does exist. It does exist. Photon scattering. I might also mention. Let me also mention a couple of other examples of closed loops. Closed loops that are important. Closed loops. Closed loops. Another thing that can happen. Here's a photon coming in. This is usually drawn like this. Hang on. Where it comes from. So let's say take this vertex, I take two basic vertices and I join them. Okay, I'm going to join them. So the way this is drawn is usually just bend them like this. So here I have a photon coming in, and again there are two vertices, and again there's a closed fermion loop. Now this you can think of as a photon can turn into an electron-positron pair that then annihilates again to produce a photon. Sometimes some people like to think of these diagrams intuitively with a kind of hand-waving argument from the Heisenberg uncertainty principle. They say, well, over a finite time, energy can't really be defined properly. So you can have sort of temporary violations of energy conservation. This kind of hand-waving language is often used. They say, well, it's possible the photon can turn into a virtual electron-positron pair that then somehow annihilates and gives a real photon again. From the point of view of quantum field theory, look, this is just some BS. This is what's going on. I have an excited photon mode, and if I look at the transition amplitudes, you get terms that can be represented symbolically like this. This actually contributes, for instance, if I have, to give you a sense of how the perturbation series works, let's say I'm looking at electron-electron scattering. And there is a term from the second order correction to the S-matrix operator that looks like this. So electron-electron scattering, they exchange a photon, and there's ion being aggregated. There is also a term from the fourth order. If you want, there's a term that contributes to electron-electron scattering that comes from the fourth order operator, which is this. So I still have my electrons coming in, electrons coming out, but the photon gets exchanged, but on the way, it does this business. So I now have four vertices. Okay, I've actually joined four vertices. So if you were going to look at the amplitude, this here is of order e squared, and this is of order e to the 4th. So now you see how the perturbation series works. If I was going to calculate electron-electron scattering. Okay, from the point of view of perturbation theory, I've got, let me make a bit more room for myself. We've got, just to give you a sense that, look, this really is a representation of a perturbation expansion. I could say, well, okay, there's my basic process of order e squared. But there are other terms. I could have, well, I could have this. I could have this. This is of order e to the fourth. They've exchanged 2 photons. Why not? And these are internal fermion lines. I can have this business. This is also of order e to the fourth. I could have this business. This kind of thing. This is of order 1, 2, 3, 4, 5. This is of order e to the 8. Okay, but I've got successively smaller. Nobody's going to work this out. A calculation like this. This is the basic term, which is pretty accurate, and then there are small corrections. Okay, and you might want to go to e to the fourth. Only some maniac is going to go to e to the 8, and it's probably not even measurable with the accuracy that we have. Anyway, so but to give you a sense of look, this is a perturbation series. A perturbation series where the higher order diagrams. So higher order diagrams with more vertices, they represent successively smaller corrections. Smaller or successively smaller contributions. So if I have n vertices, the amplitude is of order e to the n. Okay, so this kind of idea. One other closed loop I wanted to mention is another closed loop is that the electron can travel along and emit a photon and reabsorb the photon. Here there'll be a factor IDF, here there's a factor ISF. I should mention that when you get the closed loops, unfortunately you get divergences in the closed loops. Closed loops diverge. And I'll talk a bit about this more next week, but let me just say that the divergences can be absorbed in a redefinition of mass, of electron mass and charge. This process is called renormalization. So what can happen is that if you, for instance, have, well, let's say let's say again, give the example of electron scattering. Another contribution would look like this. It could be doing this. This electron on its way out has emitted and reabsorbed the photon. This contribution, unfortunately, there is a divergence. But what you can do, the basic idea of renormalization is that you define an effective mass to be the mass that appears in the equations plus a correction. Okay? This correction formally diverges. But what you can do, if you say, well, the only thing that we actually see is this effective mass, which is finite. So in other words, there's a way of sweeping the dirt under the carpet. I'll talk a bit more about that later. This subject of renormalization is a subject for a more advanced course in quantum field theory. Okay, if there was a part 2 next semester, we will go into this. But the sort of first course like this, normally you wouldn't bother to say, okay, let's stop short of these diagrams with closed loops. They only contribute higher order corrections anyway. So, you know, for most purposes, you can, you know, for practical purposes, it's certainly an introductory course, it's plenty accurate to just look at the lower order diagrams with no closed loops. But just be aware that these closed loops do cause divergences. So this creates a mass renormalization, and the other closed loop that I showed you for the photon, it actually creates a charge renormalization. That in effect, if I'm looking at, if I include this term here, then I have to define an effective electron charge, that is E plus delta E, where delta E formally diverges, and you can sort of package things in a way such that everything is written in terms of the effective charge and the effective mass, and this bad stuff that we don't like is sort of, we don't really see it, so which is not very satisfactory, but there's the state of physics today. Okay, so let's see, blah, 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 blah. What, is there anything I'm always enjoying? Okay, that's what I wanted to say about that. So, we're now going to write down, so that's the kind of, I'm just giving an idea of, okay, clearly I can join all kinds of vertices, conjure up all kinds of processes. Now we want to write down the Feynman rules. Okay, we want to write down the Feynman rules. Before we write down the Feynman rules, let me just remind you of exactly the forms of the Feynman propagators. Feynman propagators in momentum space, and B, just to remind you that the Feynman photon propagator, let's use alpha beta, the book is using alpha beta instead of mu nu. The Feynman propagator in momentum space is minus G alpha beta over K squared plus I epsilon. And the Feynman propagator, so for the fermions, that's the Feynman photon propagator. The Feynman fermion propagator in momentum space is P slash plus M over P squared minus M squared plus I epsilon. Or there's a symbolic shorthand which I'm going to explain, which writes this as 1 over P slash minus M plus I epsilon. So what the heck is that? Let me just explain. It's just a shorthand, symbolic shorthand. Just remind you, what is P slash? P slash is gamma mu P mu. It's just a shorthand for gamma, the contraction of the gamma matrix with the form with the 4 vector. So when we write, so S Feynman P is really, you know, let's write alpha, gamma alpha, P alpha. Sorry, I prefer mu and nu. All right, mu and nu, gamma mu, P mu plus M over P squared minus M squared plus I epsilon. Some people like to just write a P slash plus M. Anyway, what's this thing? What do you mean P slash? Okay, just note. So P slash squared is equal to P squared. How can we prove that? Well, P slash squared is gamma mu P mu times gamma mu P mu, which is equal to what? Well, let's just remember that the gamma matrices satisfy this relation. 2G mu nu. So if I multiply both sides by P mu, then with a little bit of fiddling, you should be able to see that this just gives me P slash squared plus P slash squared is equal to 2P squared. So in other words, P slash squared is equal to P squared. This is just P squared. All right, maybe check that through if you like. And so what does this imply? This implies that P slash plus M times P slash minus M is equal to P squared minus M squared. Why? Because I get a P slash squared, which is P squared. I get plus M P slash minus M P slash. I cancel minus M squared. So this is true. So what I can do, if you want, you can say, well, okay, I get tired of writing this. If my arm is aching, we're having to write P slash plus M over P squared minus M squared plus I epsilon. What I can do, remember that the gammas are 4 by 4 matrices. Okay, so what on earth does this mean? This is 1 over a 4 by 4 matrix. What on earth does it mean? Okay, what it means is, so here I've got the Fermion propagator. I've got a 4 by 4 matrix, and this is a number. What I can do is symbolically, well, P squared minus M squared is a number, which is in fact equal to P slash plus M times P slash minus M plus I epsilon. And then what people think, and here's where the symbolic part comes in, this is just symbolic shorthand, is you can think, well, let's cancel the P slash plus M and maybe redefine the epsilon, and I can just write this as 1 over P slash minus M plus I epsilon. That's what this. So this, but look, don't worry about this. This is just a shorthand for this. This is the expression for the Fermion propagator. It's P slash plus M divided by this. This is just a shorthand, okay? But just so you understand what the reasoning is there, why that makes sense. Okay, so now we're going to look at the finally going to look at the general structure of transition amplitudes and write down the Feynman rules. So this is a great moment in your lives. Okay, tonight you can go out and celebrate. Tell your friends all about how photons can scatter off each other. Fourth order Feynman diagram. Electron positron annihilation. All this fantastic stuff is now in your hands. So, so general structure. Of transition matrix element, or the matrix elements of the S matrix operator. We've seen some examples where we actually calculated the matrix element. We looked at the first order matrix element. We looked at an example of a second order matrix element. You've done the homework, you went through all the calculations, and you always got, in each case, you get a result. If you look at other examples, you always get the following general structure. So first of all, well, remember S is equal to 1 plus. This is, of course, really the identity operator. So the first term, the 0th order term, will give me a Kronecker delta. There's a delta Fi, which we usually ignore because we're assuming that the initial and final states are not exactly the same. But anyway, if they were exactly the same, then there's this term here that you would want. 0. Okay, so now the interesting part. What do you get? There is always an energy momentum conserving delta function with a factor 2 pi to the 4th in front. So what is this? This is the final total for momentum. This is the initial total for momentum. So imagine I've got just, not really in terms of Feynman diagrams, but just a normal picture. Imagine I've got some, I've got various particles coming in, maybe there are photons coming in, and I've got particles coming out, and I've got the initial, the total form momentum is just the sum of the form momenta of all the incoming particles, and here I've got the final form momentum, which is the sum of the form momentum of the outgoing particles. So you can think of this as the scattering or interaction region. So these particles come in from far away, we take the t is minus infinity, they scatter, and they go out, and at t is plus infinity, we measure what comes up. So, anyway, so there is this form, that just enforces conservation of total form momentum. Then we find that there are some factors. Let's write it like this. There are factors square root of m over VE for each external fermion. So if I have an incoming electron or an outgoing electron or an incoming positron, outgoing positron, each of these lines contributes a factor square root of m over VE. So, and you just write them multiplying each other if there are several of these lines. So what we can do as a shorthand, we can write this as a product over the external lines. Okay, so if I had, let's say I have this process, let's say we're looking at this process. There's going to be, let's call this P1, P2, P1 prime, P2 prime, let's call this K prime. There will be factors, the factors over the, sorry, let me finish. This is for each external fermion. Then there are factors 1 over, for each external photon, there's a factor 1 over the square root of 2v omega. So here again, I can write this as a product over the external lines. So in this case, here, this will give me a factor root m over v over VE1. Here there will be a factor root m over VE2. Here there's a factor root m over VE2 prime. Here there's a factor root m over VE1 prime. And here there will be a factor 1 over the square root of 2v omega prime. Okay, so there will be, for each external line, there's one of these factors. If it's a fermion, it doesn't matter if it's initial or final. If there's an initial or final fermion line, I get a factor root m over VE. Initial or final photon line, I get a factor 1 over root 2v omega. Okay, and these come from those factors that were in the field expansions of the operators, and that's how they end up in the matrix element. So this is the general structure, and then of course multiplied by this thing called the Feynman amplitude. Feynman amplitude. Okay, that is the general structure of the S matrix element. Okay, conservation of form momentum, factors from the external lines for fermions and for the photons, multiplied by this general thing on the Feynman amplitude, which we're going to write down the Feynman rules for. Feynman rules. Now, we've said, so here we have S, the total S. S is of course given by an expansion with its successively smaller terms. The Feynman amplitude is also given by, if you look at this, well clearly if S is expanded in a series, you know, for this to be true, M is also expanded in a series. The Feynman amplitude is equal to, so we start with then, there's no zeroth order term, the first order term, so you can write it as the first order term plus the second order term plus the third order term. And what is this? This comes from the first order correction to the S matrix operator. This comes from the second order correction. This comes from third order correction, etc. Now, what happens is the nth order perturbation, the S matrix operator, gives you an nth order term in the Feynman amplitude, and how to find, let's say, the nth order Feynman amplitude. What do? This comes from all Feynman diagrams with n vertices. So the second order part comes from Feynman diagrams with 2 vertices, third order part comes from Feynman diagrams with 3 vertices, etc. And of course the correct external lines. When I say the correct external lines, what do I mean? Let's say we're interested in electron-electron scattering. So the initial state is an electron, the final state is an electron. And I've got to say, okay, I've got electron coming in, electron coming out, and let's say I'm working to second order. You say, well, you know, what Feynman diagrams are there that have the correct external lines and that have just 2 vertices? Well, there's this one. Okay, this gives me a way of joining 2 vertices, electron scattering. If I was working to third order, let's say if I was working to fourth order, then I could have an extra line in here if there was fourth order, and so on and so on. Okay, just as I've already described. So you could have, so if I had, for instance, say I was, let me put it like this. Let me say I was doing electron scattering, doing this, plus this kind of business, etc. So what is this? This is the second order Feynman amplitude. Here I've got a fourth order Feynman amplitude. and so on and so on. So I'm just, for any given process with given initial and final states, you can just write down the contributions by constructing, well, what are the Feynman diagrams that are consistent with those initial and final states. And you can work to different orders, and this is a series, and this is the general structure. Okay, that is the general structure. So now, let us write down the Feynman rules, or let's start writing down the Feynman rules. And then on Tuesday, we're going to be applying the Feynman rules. So this is really the Feynman rules. Maybe what I'll do, I'll start over here. Let's start over here. So, I'm going to write down the Feynman rules. Okay. So Feynman rules for QED. Feynman rules for QEDs. So here, these are listed in the book in section 7.3. So it starts with rule 1. I'm going to start with rule 0, which is a rule that the book, it sort of slips in later on as part of rule 7, but I think it makes more sense to have it sort of the 0th rule. The 0th, hang on, my general structure of transition matrix elements. Okay, good. Okay, what we might sort of think of as the 0th rule is that for momentum is conserved at each vertex. So what do I mean? If I have P and I have P prime and K prime is a vertex, then P is equal to P prime plus K prime. This is true even if this is an internal line. So if I have, for instance, let's say I have this business here. I have P coming in, P coming out. Here's a momentum K. This virtual photon has a full momentum K. The internal line for the fermion, this has, so here I've got P coming in. This has momentum P minus K. Okay? So think of it as, remember, it's not a space-time diagram, it's sort of abstract diagram. But you can think of it as like currents in a wire. If I have different wires coming in and joining somewhere, so there's a current P coming in, there's a current K coming out, a current P minus K coming out into this node or this vertex. So, so for example, okay, for momentum is conserved at each vertex. Then rule number 1, each vertex, so for each vertex, write a factor, i.e. gamma alpha. So we've already seen a couple of examples where a vertex contributes a factor, i.e. gamma. 2. For each internal photon line, write a factor I d Feynman alpha beta K. Okay? Right, the factor is just I times the Feynman photon propagator. So for each internal photon line, perhaps I should have said for each internal photon line with momentum K, so for instance in this example, there's an internal photon line with a form momentum k, then you write a factor ID Feynman where the argument of the Fermion propagator is the k that appears in that line, okay, obviously. So, 3. For each internal fermion line with form momentum, when I say momentum, I mean form momentum with momentum p, so we write a factor Is Feynman of p. Remember that this is a 4x4 matrix. Then rule number 4. So I'm going to stop here at number 4. There's also number 5, 6, and 7 to do with loops and things that we're going to look at next time. But let me just write down here because this is a bit of a... okay, for each external line, write factors. So it depends exactly what kind of line it is. If I have an initial electron, if it's an initial electron, I write a factor UPR. If it's a final electron, I write a factor U bar PR. If it's an initial positron, I write a factor V bar PR. If it's a final positron, I write a factor V PR. Notice that here the initial and final electron, I've got U and U bar, whereas for the initial and final positron it's the other way around, it's the V bar and the V. We'll see this is why you have to have the arrows pointing backwards on the external positron lines. We'll go over this next time. For each initial photon, there is a factor epsilon k alpha, and for each final photon there is the same, sorry, this is a 4 vector, there is a factor epsilon k alpha, where these p's and r's, k's and r's, they label the momenta and spins and polarizations of these external particles. So, and then, okay, let me write down rule 5 here. Let me write down rule 5. The spinor factors. So in other words, the gamma matrices, the S Feynman, the U's and the V's are ordered like this. So if you reading from right to left, reading from right to left, they occur in the same sequence as following the arrows on the fermion line. So if I have something like this, let me just, let's say I have something like this, when I write down these factors, I write them from right to left, but I follow the direction of the arrows. So if it's an electron, the arrows go this way. If this was a positron line, so I have a positron coming in, emitting and reabsorbing a photon. Time goes this way. Time always goes from left to right. But when I write down the spinor factors, I write down these factors here. I start from the right, I read from right to left, but as I write them down, I follow the direction of the arrow. So I'll write down, for a final positron, we write down V. So I would first write down a V, and then I would write down I gamma, blah, blah, and then the initial positron line, I write down a V bar. And we'll end up with something that actually gives you complex numbers. I go to V bar times the matrix times V. So it's important, this is why the arrows have to point backwards here. So the factors are ordered, reading from right to left, following the same sequence as the arrows on the line. Next time, Tuesday, we're going to do lots of examples. We're going to look at lots of diagrams. I'm going to finish the Feynman rules. There are another 2 Feynman rules, 6 and 7, that are for closed loops, which we're not really going to need, but still you need to know. But the Feynman rules you really need to know about and work with are here. We're going to add a couple of Feynman rules to deal with closed loops, which will really come up in a more advanced course. And we're going to look at lots of examples. We're going to write down a diagram, we're going to use the rules, write down the Feynman amplitude, we're going to calculate scattering cross sections, do all kinds of things. So there we are. That's it for this week. So if there are any questions, I'll hang around a bit here. Please email me for an office hour if you need any help. Or are there any questions? Quick questions? Any quick questions? Probably 1,000 long questions. If there are 1,000 long questions, please see me for an office hour. And anyways, a great day. Celebrate tonight. Feynman rules for QED, fantastic. Now you can go out in the world and calculate all these amazing things. So there we are, a few beers, being well.